Okay, greetings, aspiring scientists. Welcome to my lecture on states of matter and temperature. We will continue where we left off last time on the classification of matter. These things are very much connected, as I'm sure you can imagine. So this is 1.1.2 in the IB chemistry curriculum, if you would like to refer to that. So states of matter. Most of you probably think you're quite familiar with this, and you probably are, but maybe you might learn a few things from my lesson today. So states. Matter is made of small particles called atoms, molecules, or ions, and matter is usually found in one of three states: solid, liquid, or gas. You probably have heard of other states such as plasma or Bose-Einstein condensate or some other rare types of matter. But these are the main ones, most common under standard conditions. So some things about this. I have some visual representations of these generated by ChatGPT, but I think they're pretty good. So solid on the left. If you put a solid object in a container, not much will happen, right? It retains its shape, and although you can't really see it, those atoms that are in a solid, atoms or molecules, are moving, they're vibrating, but they're not changing their position on average, right? They're just moving back and forth. Now, we can melt a solid by inputting energy into it. We can make it a liquid. If you put a liquid into a container, whatever volume of liquid you start with will be equal to the volume of liquid that appears in this new container. Its volume is kind of set and doesn't change. But due to gravity, it will fall to the bottom of this container, right? Similarly, for solid, due to gravity, it rests on the bottom of the container. So liquid atoms are flexible in their position. They are vibrating as well, but they're also free to kind of move around each other, but they are attracted to each other in such a way that they're not free to move to the top of this container outside of the liquid, right? We can change a liquid into a gas by inputting more energy and really break apart those atoms from each other. So gas particles, we can say, have free position. They're able to go anywhere in this container at any time, and it has an expanding volume. It fills its container to whatever volume that is. So that's interesting. It seems to not be affected by gravity as much. Of course, those particles are affected by gravity. It's just relative to their kinetic energy. I think the effects of gravity are not very significant. All right. Now, that's not the end of the states chapter, but I feel like it doesn't make a lot of sense to talk about changing states before we talk about temperature. So temperature is 1.1.3. We'll also discuss that here. So temperature. I'm sure you're familiar with it. You know, a hot day versus a cold day, a hot stove versus a cold ice cube. But we really need to define it and understand it more deeply. So temperature is a measurement that is directly proportional to the average kinetic energy, the average, or the energy of movement of a sample of particles. Now, the IB textbooks and curriculums for chemistry often just say temperature is a measure of kinetic energy. And I used to just teach my students that temperature is the average kinetic energy of a sample. But that's not true. Temperature is directly proportional to average kinetic energy for a gas here. Through the formula, kinetic energy, EK, equals 3 over 2, nRT. You do not need to know this equation in chemistry. You just need to know EK proportional to temperature. But if you're in physics, which probably some of you are, you will need to know how to use this equation. I think it's in the data book, so you don't need to memorize it, but this is a relationship that relates temperature of a gas to its average kinetic energy. So 3/2 is just a number. That's 1.5, 3 divided by 2. N is the number of moles of a gas. So we don't know what that is yet. We haven't learned, but it's a depiction of how many particles and how much gas you have. So really, for a single sample, it should be constant. R then is what's known as the universal gas constant. It's about 8.31 joule per Kelvin per mole. Again, we haven't learned that yet, but it's something that will sort of transform our moles of gas N and our temperature T into a kinetic energy. So without doing that transformation, temperature is not a measure of energy. And what temperature actually is, it's kind of a funny story, I think. So you guys maybe know the Celsius scale. I think that was defined by having a tube of glass with some kind of liquid, maybe mercury or some metal that expands when it is hotter and contracts when it's cooler. And that was put in some ice. When that liquid metal contracted down low, they said, okay, let's set that to 0, specifically when water is becoming ice or freezing. And they made a little mark on their instrument, and then they said, all right, let's heat this up to its boiling point. They heated the water up to 100 degrees. It started to bubble, and they said, all right, let's mark this as 100 on our little instrument here that contains an expanding compound. And that was basically the first thermometer. And they have this scale now, 0 and 100, and they just evenly cut 100 lines in between those 2 points. And they said, okay, we'll call this the Celsius scale. And a gap between those lines is 1 degree Celsius. Now, as we learn more about temperature, we realize things can get a lot colder than the freezing point of water. And, we can get minus 100, minus 200, minus 250. That you can keep going lower. And so later on, we developed the Kelvin scale. But 1 Kelvin, a change of 1 Kelvin is the same as 1 degree Celsius change. So what really is happening here is that the R gas constant is a property of the way that we defined 1 degree of temperature. It really came about due to the instrument that was designed, the first thermometer. But you could imagine it could be something totally different. It could have been, a disc of some expanding metal, like aluminum or whatever, and maybe that disc would expand its area and radius. Maybe someone measured that change instead. And if that is also directly proportional to the change in kinetic energy, that could be used as a measure of temperature on its own scale. It would no longer be Celsius or Kelvin, and that means that the R constant in this equation would change. It would not be 8.314 anymore. But I just want you to get the idea that this equation and the relationship between Celsius, Kelvin, and average kinetic energy is a bit arbitrary based on how humans decided to try to measure it. You don't really need to know that for the IB chemistry curriculum, but still I think it's interesting to think about. Alright, so temperature is officially SI units measured in Kelvin, okay? Where 0 Kelvin is absolute zero, which is a theoretical sample that has no movement of its particles. So you might remember when I introduced matter in the previous video, I said it has volume, it takes up space, it has mass, and it's in perpetual movement. So something at absolute zero actually has no movement anymore, or no vibration, but it's a theoretical sample, right? We have never actually observed anything at absolute zero. We've tried to get there, but we can only get, we can get very close, but we can't actually get there because a lot of weird things potentially happen at absolute zero. There would be zero movement, zero temperature, zero pressure. Various things that just sound kind of oxymoronic or impossible. Anyway, it turns out that delta 1 Kelvin, or a change of 1 Kelvin, an increase or a decrease, is the same as a change of 1 Celsius. So the amount is actually identical. It's just that where the scale starts and finishes is different between Kelvin and Celsius. 0 degrees Celsius is equal to 273.15 Kelvin, and therefore minus 273.15 Celsius is equal to 0 Kelvin. They have a difference in scale by 273.15. So here are some plots that sort of describe what I just mentioned. If we plot temperature in Celsius on the x-axis versus volume in liters, I guess, you can see that at 0 Celsius, where there's a dotted line through the middle here, we don't have 0 volume. We have some volume, and that should make sense. You can look outside on a cold winter's day, and the gas outside your house has volume, right? It's only at absolute zero where something goes down to 0 volume, and it's like it's compressed so hard that the volume essentially disappears. I don't know what that means. You don't know what that means. Scientists don't know what that means, I think, but it's a theoretical idea. Similarly, for pressure, at 0 degrees Celsius in the middle, a sample still has pressure. Again, you can look outside on a cold winter's day and the atmosphere still has pressure on things around it. But when you get down to absolute zero, minus 273.15 Celsius, or 0 Kelvin, there's an idea of zero pressure. Things would no longer be moving. They wouldn't have a volume, whatever that means, and they wouldn't apply any pressure on the walls of a container that they're in. So some weird ideas, but you can see that these graphs are a straight line, right? There is direct proportionality between these things, between temperature and pressure, and temperature and volume. If you double the temperature in Kelvin anyway, you should double the pressure. If you half the pressure, you half the temperature. If you double the volume, you double the temperature. If you half the volume, you half the temperature. Those statements assume that every other variable, such as number of gas particles or whatever, stays constant. And again, those statements rely on the fact that I would be talking about Kelvin temperature and not Celsius. So here's what the graph looks like actually with Kelvin on the x-axis, no longer Celsius, so no line at 273 Kelvin. So this is a direct proportional relationship, a straight line. It goes through the origin of 0, 0. So 0 temperature Kelvin reflects 0 volume at absolute zero. These are statements that you can make about directly proportionally related variables. All right. You guys might have seen this kind of plot before. This is a temperature and state change. It's an energy input on the x-axis versus temperature in degrees Celsius graph. So you can imagine we hook up a container of water to some heating power source and we input energy to it. As we input energy, this water will travel through different states and different temperatures. Okay, so before its freezing point, it's a block of ice. Its molecules are vibrating slightly, but as we input more energy, they start to vibrate more and more. At a certain point, at 0 degrees Celsius, that's the melting point. So they're vibrating so much that they start to separate from their crystal structure. They're still very much attracted to each other, but they become more free in the sense that they can move around as a liquid. So we melt our water. As soon as it's done melting, So during the melting phase, there's actually no change in temperature. It stays at 0 degrees Celsius. You can try an experiment yourself, but you should find a melting ice cube or whatever stays at 0 degrees Celsius. Then, when it's all a liquid, though, if we keep inputting more and more energy, the temperature must rise. So we get a line with a slope in the middle. It will rise and rise and rise until we get to the boiling point of water. We'll keep inputting energy, though. It starts to boil. So those liquid water molecules, some of them will group up and get enough kinetic energy to break any type of attraction that they had for each other, and they leave as free gas particles. So during the boiling, the temperature stays the same at 100 degrees. Only when all of the liquid has boiled do we see an increase in the temperature of the gas as we input more and more energy. So that's called boiling. You can go in reverse of this process and remove energy from this sample. You can condense a gas back to a liquid. There'll be no temperature change during the condensing phase. You can remove energy from a liquid. It will lose temperature all the way down to its freezing point, and then it can freeze back into a solid. During the freezing phase, however, though, there is no temperature change. Other important vocabulary. Endothermic. Hugely important vocabulary word. You can use it in almost any unit to describe various processes. This is a process which absorbs energy from the surroundings. So the surroundings must provide some kind of energy to a process that's endothermic for it to proceed forward. Exothermic. If you know any Latin, you might know endo means to go in, I think, and exo means to move out. So a process which releases energy to the surroundings. Energy moves out of your sample into the surroundings. Evaporation. This is a type of slow boiling that only occurs at the surface of a liquid at any temperature. So you know, a cup of water at like 20 degrees Celsius, even though it's not anywhere near its boiling point of 100 degrees Celsius, the volume will reduce as you leave it over several days. And that's because there's evaporation happening at the surface, where every once in a while, some particular atoms, might have a collision with several atoms nearby that gives that particular atom enough energy to escape any intermolecular forces and become a gas particle. This happens very infrequently at lower temperatures, but it still can happen, and over time, liquid samples can evaporate. All right. Deposition. This is another state change. This is directly changing from a gas to a solid, skipping the liquid phase. And this can happen under certain conditions for certain chemicals. But you have to know the vocabulary word. Deposition, gas to solid. If you know the word deposit, it's like put in. You can think of it as we're putting gas particles into a solid phase. The opposite of that then is sublimation, subliming. This is a state change from a solid to a gas, directly, again, skipping the liquid phase. Something like iodine, I2, is commonly used in the laboratory to show this. It tends not to become a liquid at atmospheric temperature and pressure, but when heated up a little bit, it forms gas instead of liquid. Okay, so let's add a couple of these things to the graph I showed you previously. Melting. This must be an endothermic process. We are taking energy from the surroundings, from our energy input, to break apart the crystal lattice of a solid. Freezing is then exothermic. This is really weird. You don't think of water freezing into an ice cube as releasing energy or releasing heat, but it actually does if you were to measure the surroundings as an ice cube is forming, or any ice. Boiling then is endothermic. We're trying to give liquid particles enough kinetic energy to separate from the mix, from the liquid aggregate, and become gas particles. We need to input energy from the surroundings to do that. Condensing then is exothermic. As a gas condenses into a liquid, for example, on the side of your glass or on your window, that process will actually release energy and heat. So we can now think about this. Which has more energy, a gas, a liquid, or a solid? A gas has the most energy. It took the most energy to produce a gas from a solid, for example. You had to break apart the crystal lattice and then break apart all intermolecular forces in order to separate individual gas particles. So in the end, gas particles contain sort of the most energy, you can say. Liquids contain a medium amount, solids contain the least. Practice questions. Let's try. Explain why temperature measured in Kelvin is directly proportional to the average kinetic energy of a sample, but temperature measured in Celsius is not. So there's several ways to answer this. But I would say direct proportionality has the property that when you double one of the variables, the other doubles. When you half one of the variables, the other halves. And this is not true when you compare Celsius to average kinetic energy, okay? And the best way to think about that is think about a change of 1 degree Celsius to 2 degrees Celsius. That is technically doubling your degrees Celsius. But you know that that change doesn't actually mean much of a change in your sample, right? The kinetic energy of the molecules in your sample have not doubled when you go from 1 Celsius to 2 Celsius. But when you go from, for example, 1 Kelvin to 2 Kelvin, or 100 Kelvin to 200 Kelvin, doubling that actually does double your kinetic energy, according to the equation I showed you a couple slides ago. So it also must be true that to be directly proportional, 0 of one must mean 0 of the other. That's that point on the far left of the graph. So 0 Celsius does not mean 0 kinetic energy. It doesn't mean 0 pressure or volume. Those properties are only true when you measure temperature in Kelvin. Okay, so that's how I would answer that. Practice question 2. In the energy input versus temperature graph of water, discuss why the horizontal constant temperature line at the boiling point is longer than the one at the melting point. So at 100 degrees, the horizontal line is longer than at 0. So we know that that horizontal line represents state changes. What does it mean if the horizontal line is longer? Well, look at the horizontal axis. Energy input. So if your horizontal line is longer, that means it requires more energy input. So it requires more energy to change water from a liquid to a gas than it does to change ice from a solid to a liquid, to liquid water. That's something you can infer or conclude about the length of those constant temperature sections. Alright, this practice question is more about my previous video. When I suddenly decided to split that video into two, some of these practice questions now refer to the previous video, but still, I think we can try this. Which of the following can be separated with physical methods? Oxygen and carbon dioxide in the air, hydrogen and oxygen in water, carbon and oxygen in dry ice, which is solid CO2, or magnesium and sulfur in magnesium sulfide, MgS. Well, you can think about that for a minute, but what are the differences between these options? So we can see the bottom two have chemical formula, CO2 and MgS. B will also have a chemical formula. It's just not shown because I'm assuming that you know water has the chemical formula H2O. A, these things also have chemical formulas. Oxygen is O2, carbon dioxide is CO2. But what you'll notice is that nothing that we are trying to separate in A is chemically bonded. So the answer is A. Oxygen and carbon dioxide can be separated by physical methods, perhaps cooling down to one of their boiling points or condensing points. They should be quite different. Or even centrifuging, they have different masses, although that's probably quite inefficient. But the other things, you're going to be trying to separate, hydrogen from oxygen in water. They are chemically bonded together. They can't be physically separated. Carbon and oxygen in dry ice, same thing. Magnesium and sulfur in MgS, same thing. You need to do chemical processes to separate those. All right, so that brings us to the end of this section. Remember our guiding question that I introduced in the previous video. How can we model the particular nature of matter without being able to easily directly observe all these things? Well, we model atoms as kind of these little particles, right? We've been drawing them as little circles or balls, and the analogies that we have of like little balls connected to each other with sticks or bonds generally work to help us answer most of the questions in this section, comparing how those little particles move as gases versus liquids versus being locked in place as solids. Considering that those have energies of movement, which is related to their temperature. We model that with an equation that I showed, EK equals 3 over 2 nRT. That's a mathematical modeling of this that also makes assumptions about ideal gases and things. But we'll discuss that later. But I think you should be able to answer this question fairly well after watching my 2 videos about this. All right, so we'll move on next time to the next section, which is more about the nuclear atom. I hope to see you in the next video. Leave any comments if you have any questions or requests. Thank you so much. See you next time.